Hello there, welcome to the Science Owl Station channel. Today, we begin a quiet journey toward the heart of our own cosmic neighborhood, to the silent, majestic engine that has illuminated our days and shaped our very existence since the first spark of life stirred. I invite you to close your eyes, if you wish, and picture not the blinding midday glare, but the gentle, warm glow of a sunrise just peeking over a calm horizon. For we are going to visit our sun. Before we delve into the numbers and the nuclear furnaces, let us simply feel its presence. Wherever you are right now, whether it's late night where you are or perhaps early morning, if you're listening from a bustling city or a quiet countryside, take a moment. Feel the space around you. Some 8 minutes ago, a tiny fraction of that warm, ancient light left the sun's fiery surface. It traveled silently, unfathomably fast across 93 million miles of utter void, slipped past the moon's silent vigil, danced through the high atmosphere of our blue world, and found its way, perhaps through your window, perhaps simply as the idea of day. That light, now a soft memory in your mind's eye, is our tether. It is the most constant visitor in human history. What is this glowing entity we so take for granted? We call it a star, an ordinary, middle-aged, rather unremarkable star amongst the hundreds of billions in our galaxy alone. And yet, to us, it is everything. It is the definition of ordinary turned into the most profound miracle. It is not a solid, rocky world like our own, but something far more ethereal and dynamic. A colossal, slowly swirling sphere of incandescent gas, held together by its own immense gravity and shining from the energy of atoms fusing in its core. It is, at once, a simple ball of light in our sky and one of the most complex and powerful physical laboratories in the cosmos. The story is our story. The iron in your blood, the calcium in your bones, the very oxygen you breathe. These atoms were forged in the hearts of stars that lived and died long before our sun was even a glitter in a nebula's eye. Our sun is a later generation star, a gatherer of ancient stardust. It coalesced from a collapsing cloud of that recycled gas and dust about 4.6 billion years ago, and in its stable, enduring glow, it cradled the formation of our Earth and all its siblings. It doesn't just allow life, its consistent rhythm invited life. The predictable arc of its journey across our sky gave us days and seasons. Its warmth creates the gentle churn of our atmosphere and oceans. Its light feeds every green leaf, which in turn feeds the world. So, as you settle in, let your breathing slow to a peaceful rhythm. Let's set aside the chores of the day, the glow of other screens. Imagine, instead, floating in the deep, quiet blackness of space. It is cold here and still, and then, in the distance, a presence. Not a sharp point of light like the stars, but a soft, overwhelming sphere of pure, gentle radiance. It doesn't flicker, it doesn't waver. Simply is, a perpetual, comforting hearth in the cosmic night. This is our starting point, a feeling before a fact, a recognition of that familiar, golden disk not as a harsh light, but as a distant, nurturing ember. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. The journey of understanding our sun is not one of conquering a distant frontier, but of coming home to a truth that has always warmed our skin. We begin not at its ferocious core, but at the very edge of its influence, in the calm where we reside. Picture the solar system not as a flat diagram, but as a vast, spherical field of gentle influence. At the very center of this invisible sphere rests our star. Its gravity is the master conductor of a slow, silent symphony. Every planet, from speedy little Mercury to distant, drifting Neptune, moves to this timeless pull. Every asteroid tracing its elliptical path, every comet with its glorious tail pointing away from the solar wind, they are all bound in this graceful, eternal dance. The sun does not demand. It simply holds, with the quiet, assured strength of a gravitational embrace that spans billions of miles. It is this embrace that gives our cosmic address its order, its predictable harmony. And we, on our pale blue dot, are cradled within the most delicate, fortunate band of this embrace. Not too close to the heat, not too far into the cold. A perfect, distant seat by the universal fireplace. To truly appreciate our sun's nature, we must first step back. Far, far back. Let us gently untether from that comforting gravitational embrace and drift backwards, as if on a slow, silent current, away from the warmth of our celestial hearth. Watch as the planets shrink, becoming mere glints of reflected light. The asteroid belt fades into a faint, dusty memory. We pass the icy sentinels of the Kuiper belt, and even the distant, mysterious sphere of the Oort cloud becomes a hypothetical haze, until, at last, our entire solar system is just that, a system, a single, intricate clockwork mechanism held in the palm of a golden, glowing hand. And now we let that hand itself shrink into the distance. We find ourselves adrift in a sea of stars, but not a random scattering. A majestic, swirling pattern emerges from the darkness. We are now seeing our home galaxy, the Milky Way, from a perspective few human eyes have ever truly imagined. It spreads before us like a colossal, slow-motion whirlpool of starlight and cosmic dust. Its spiral arms etched in the glowing pink of stellar nurseries and the deep blue of brilliant, young stars. It is breathtakingly vast, containing perhaps 100 to 400 billion stars. And here, in this grand design, we must search for our own. Our sun does not reside in the bustling, dense core, where stars crowd together in a brilliant, frenetic ball. That center, hidden from our earthly eyes by great clouds of dust, is a place of ancient, red giants and mysterious, powerful forces. Instead, our sun lives in the galactic suburbs, out along one of the quieter spiral arms. This is the Orion Arm, or sometimes the Orion Spur. It is not one of the galaxy's major, bold arms, but a smaller branch of stars, gas, and dust that lies between the immense Perseus Arm and the grand Sagittarius Arm. We are, cosmically speaking, on a quiet, leafy side street of a vast stellar metropolis. From our vantage point here on Earth, when we look toward the constellation Sagittarius on a clear, dark night, we are peering in the direction of that brilliant, crowded galactic center, some 26,000 to 28,000 light-years away. Let that distance settle softly in your mind. A light-year is not a measure of time, but of distance. The distance a particle of light travels in one Earth year, moving at 186,000 miles every single second. The light from the galactic center that touches your eye on a summer night began its journey when the last ice age still held much of our planet in its grip. Our sun, and us with it, is remarkably far from the heart of things. And yet, we are not stationary. Our sun is not a fixed lamp in a galactic room. It moves, It carries its entire planetary family along with it on a slow, stately journey around the galactic center. This is our true grand orbit, one that makes our year-long trip around the sun seem like the briefest heartbeat. Traveling at about 140 miles per second, it still takes our sun approximately 230 million Earth years to complete one single revolution around the Milky Way. This timescale is known as a galactic year. Consider this the last time our solar system was in this particular position in the galaxy. The great age of dinosaurs was just beginning on Earth. In the entire history of complex life on our planet, we have not even completed one full galactic circuit. This motion is not a simple, flat circle. As our sun orbits, it also bobs gently up and down, crossing the galactic plane like a dolphin slowly arcing through the surface of a cosmic ocean. This cycle takes about 30 to 40 million years. Some scientists muse that this rhythmic motion might influence Earth's climate over deep time, as we pass through different densities of interstellar gas and dust, potentially affecting the cloud of comets in the distant Oort cloud. But this is a slow, gentle rocking, not a violent plunge. What is our immediate neighborhood like? Even within our quiet spiral arm, space is not a perfect vacuum. Our sun is currently passing through a region called the local interstellar cloud, a wispy, tenuous patch of slightly denser gas and dust, about 30 light-years across. We entered it perhaps tens of thousands of years ago and will drift out of it in another 10,000 to 20,000 years. The difference is minuscule, the gas so thin it makes the best laboratory vacuum on Earth seem as thick as syrup. But it is a reminder that we are sailing through a galaxy that has texture, variation, and history written in its faintest breezes. So picture it now from this new, vast perspective. Our vibrant, dynamic sun, with its storms and flares and loving light, is but a single, gentle golden pearl stitched onto a spiral arm of a glittering disk. It is a traveler on a road so long its beginning and end blur into the deep time of the universe. This vantage point is not meant to diminish our star, but to frame it. Its grandeur is not lessened by its galactic modesty. Rather, its steadfast, reliable nature becomes even more precious. In the immense, slow-churning wheel of the Milky Way, it has provided a fixed point of warmth and consistency for a tiny, rocky world. A world that, from here, is invisible, a dream of dust and water clinging to a mote of light. It is a humbling and peaceful thought. Our entire history, all our triumphs and tragedies, our art and our science, the rise and fall of civilizations, every person who has ever lived and loved, all of it has unfolded on a platform hurtling through the void, steadied only by the constant pull of a modest star in the quiet outer realms of a spiral galaxy. And that star, in turn, is just one of multitudes, performing its own slow, graceful dance in the immense velvet dark. As we drift back from that vast, galactic panorama, letting the swirling arms of the Milky Way soften into a distant haze, we gently guide our focus back to the single, gentle pearl of light that is our sun. From the incomprehensible scale of its journey, we now turn inward, not to its ferocious core yet, but to its very essence, its substance. What is our sun made of? If we could reach out and gather a handful of its being, what would we hold? The answer is one of beautiful, profound simplicity, a cosmic recipe written in the first few minutes of the universe itself. The sun is not fire, as the ancients thought. It is not solid rock or molten iron. It is a sphere of plasma, a fourth state of matter, beyond solid, liquid, or gas. Here, the temperatures are so ferociously high that atoms are ripped apart. Electrons are stripped from their nuclei, creating a swirling, electrified soup of subatomic particles. But the ingredients of that soup are remarkably straightforward. In terms of mass, our Sun is about 74% hydrogen and about 24% helium. Those two simplest, lightest elements account for roughly 98% of everything our star is. The remaining 2% is a faint sprinkling of heavier elements: oxygen, carbon, neon, iron, and others, elements that we and our Earth are intimately familiar with. This is the first quiet fact to hold. Our Sun is a near-pristine cosmic artifact, composed almost entirely of the two primordial elements forged in the Big Bang. Let us contemplate hydrogen for a moment. It is the universe's fundamental building block, the first element to condense out of the cooling energy of creation. A hydrogen atom is simplicity itself. A single proton as its nucleus, with a single electron dancing around it. In the Sun's unimaginable heat and pressure, these atoms are denuded of their electrons, leaving bare protons swimming in a sea of energy. This is the star's primary fuel. Helium, the second ingredient, is the ash. A helium nucleus is composed of 2 protons and 2 neutrons, a stable, tight bundle forged under extreme duress. The story of the Sun, and indeed of all stars, is the story of patiently, relentlessly turning hydrogen into helium. Imagine the Sun's composition not as a static mixture, but as a dynamic, layered tapestry. From its core to its outer atmosphere, the ratios shift subtly. In the very heart where the alchemy happens, the proportion of helium is steadily increasing as hydrogen is consumed. Over billions of years, the core becomes richer in this helium ash. This slow change is the key to the star's long life and its eventual fate. But for now, the blend is perfect for sustaining its gentle, life-giving glow. How did this specific mix come to be? Our Sun is a star of the 3rd generation. The first stars, known as population 3 stars, were behemoths made of pure hydrogen and helium from the Big Bang. They lived fast, brilliant lives and died in spectacular supernovae, blasting the first heavy elements, like carbon, oxygen, and iron, into the cosmos. These elements mixed with the primordial gas. A second generation of stars formed from this slightly enriched material. When some of those two exploded, they further seasoned the interstellar clouds. Our Sun coalesced from a cloud that had been thus enriched by countless stellar generations. The iron in our blood, the silicon in our rocks, the oxygen in our water, all those trace elements in the Sun's 2%, are gifts from stars that died long before our solar system was born. Our Sun, in its composition, is a living archive of galactic history. Consider the sensory experience of this substance. If you could somehow stand within it, what would it be like? There is no surface to stand on, no solid ground. It would be like being immersed in a dense, radiant fog. A fog of unimaginable heat and light. The pressure would be immense, a constant pressing presence from all directions. You would not hear the roar of fire, but perhaps a deep, pervasive hum, the sound of countless collisions and rippling magnetic waves. It is a body not of rock, but of churning energy and matter in its most dissociated primal form. It is a continuous, slow-motion explosion held in perfect balance by gravity. This composition dictates everything about the Sun's behavior. The preponderance of hydrogen sets the duration of its stable life. The tiny fraction of heavier elements, which astronomers call metallicity, influences its temperature, its magnetic activity, and even the potential for planets to form around it. A star with significantly lower metallicity might not have the dusty ingredients to form rocky worlds like our own. In this way, that faint 2% trace is not an insignificant detail. It is the reason we are here to ponder it. So, as you settle deeper into relaxation, picture this. A sphere of light 93 million miles away is at this very moment a vast, slow-motion crucible. Within it, the simplest atoms in the universe are engaged in a dance of transformation that has lasted 4.6 billion years and will continue for billions more. It is a dance of purity and recycling, of ancient inheritance and steady, predictable change. The hydrogen is the kindling, the helium the soft, accumulating embers. And those trace elements, the legacy of dead stars, are the subtle spices in a cosmic recipe that resulted, against all odds, in a world of green and blue, and in a quiet moment like this, where we can listen to its story. It is a reminder that we are connected to the sun not just by its light and warmth, but by shared substance. The atoms in your body right now, save for the hydrogen, were once inside a star. And the hydrogen, that is the oldest material of all, a direct link back to the dawn of everything. We are literally stardust dreaming of the star that now sustains us. As we cradle the knowledge of the sun's simple elemental nature in our minds, let us now gently expand our sense of scale. We move from the microscopic realm of protons and nuclei to a measurement more tangible, yet still almost ungraspable, its sheer physical size. This is where numbers cease to be mere figures and must be transformed into feeling, into imagery. So, let us breathe slowly and imagine ourselves as cosmic artists, sketching the dimensions of our local star. The most fundamental number is its diameter, approximately 1.39 million kilometers. Say that number softly, 1.39 million. It is a figure that the rational mind can write down but struggles to truly feel. So let us begin with a comparison that is almost a meditation. Picture our Earth, a vibrant marble of blue, white, and swirling green. Now imagine you could place Earth side by side in a line. To span the diameter of the sun, you would need to line up about 109 of our planets, one after the other. But this linear measure, while impressive, doesn't capture the full volume, the true spaciousness within that glowing sphere. This is where the mind can softly boggle. The sun is not just longer, it is overwhelmingly more voluminous. If the sun were a hollow sphere, a vast golden cosmic bubble, you could fit roughly 1.3 million Earths inside it. Pause on that image. Not 1,000, not 100,000, but 1.3 million entire worlds. All the oceans, all the mountains, every city and forest and desert, every human who has ever lived could be contained 1.3 million times over within that single serene ball of plasma. It is a thought that dissolves the ego and invites a quiet awe. Our entire world, with all its complexity and drama, is but a single tiny pearl in a chest filled to overflowing with identical pearls, all contained within our star. Let us try another gentle analogy. If the sun were scaled down to the size of a standard beach ball, say about 1 meter in diameter, then Earth on the same scale would be about the size of a small green pea or a peppercorn, roughly 9 millimeters across. And the distance between them? On this scale, that peppercorn would be orbiting about 107 meters away, roughly the length of a football field. You would hold the glowing beach ball, and the tiny pea representing our home would be a full sprint away. This separation is the key to life. It gives us the gentle, diluted version of the sun's power, the diffused light and warmth we need, not the overwhelming furnace at close range. But the sun's size is not just an empty volume. Its immense scale is the direct cause of its profound gravity, which we feel as the gentle, constant pull that keeps us in our yearly orbit. That gravity is a function of mass, and the sun's mass is the anchor of our solar system. Yet, despite its staggering volume, the sun is not equally dense throughout. In fact, its average density is about 1.4 times that of water. This means that if you could find a bathtub large enough, a bathtub the size of a solar system, and fill it with water, the sun would, on average, barely sink. It would float like a celestial apple. This is because it is a gaseous sphere, fantastically dense and compressed at its core, but becoming exponentially more ethereal and diffuse as you move outward through its radiant layers. Its size is therefore deceptive. It is a vast, tenuous body with a phenomenally dense heart. Now, close your eyes and try to hold this image. Not the blinding disk you must avert your eyes from at noon, but a soft, golden sphere hanging in the perfect black velvet of space. Feel its scale as a presence, not a number. It is a sphere so large that light itself, the fastest thing in the universe, takes about 4.6 seconds to travel from its left limb to its right limb across its face. A single photon, traveling at 186,000 miles per second, would need nearly 5 full seconds to traverse the star's girth. Imagine that journey from the photon's perspective, a timeless streak through a golden haze of plasma, a brief but epic voyage across the face of its creator. This immense size also dictates its appearance in our sky. It appears almost exactly the same size as the moon, a coincidence that grants us the breathtaking beauty of total solar eclipses. This perfect celestial alignment is a fleeting gift of our current epoch, a harmonic convergence of distances and diameters that will not last forever, as the moon slowly drifts away from Earth. For now, it allows the delicate, pearly corona, the sun's outer atmosphere, to be revealed, a halo of ethereal light around a perfect black disk. This spectacle is only possible because of the precise geometry born from these specific sizes and distances. So, as we let these scales settle in our consciousness, we arrive at a peaceful, humbling realization. The sun's grandeur is not aggressive or imposing in the void. It is a gentle giant. Its size is the reason for its steady, enduring burn. A smaller ball of gas would have collapsed into a hotter, faster-burning frenzy or a cool, dim ember. A larger one would have consumed its fuel with lustrous, deadly speed. Our sun's size is just right for the long, slow, stable simmer that planetary life requires. Its vastness is not for intimidation, but for longevity. It is the cosmic equivalent of a deep, slow breath held for billions of years. And we, on our peppercorn world, bask in the steady, patient glow of that breath, forever held at a safe and perfect distance by the gentle mathematics of gravity and space. Having felt the serene, encompassing volume of the sun, we now turn to a quality that is even more fundamental, yet entirely intangible: its mass. This is the true source of its silent authority, the reason for the graceful orbits that structure our solar system. If its size is the canvas, its mass is the hand that holds the brush, painting the motions of worlds with invisible, gentle strokes. So, let us contemplate not what the sun occupies in space, but what it weighs in the cosmic balance. The number, once again, is one that stretches the imagination. The sun's mass is approximately 1.989 times 10 to the power of 30 kilograms. To translate that from scientific notation into a feeling, we can say it is about 333,000 times the mass of our Earth. But a more profound perspective lies in its share of the entire solar system. The sun alone accounts for a staggering 99.86% of all the mass contained within the sun's gravitational domain. Everything else, all the planets, moons, asteroids, comets, and the dust drifting in the spaces between, comprises a mere 0.14%. This is perhaps the most humbling fact of our cosmic neighborhood. All the majestic worlds we marvel at, the giant, banded Jupiter, the ringed elegance of Saturn, our own vibrant Earth, are but cosmic afterthoughts in terms of sheer substance. They are the crumbs left over from the star's formation, the slight excess that didn't fall into the central furnace. This overwhelming concentration of mass is the sole reason for our existence within an ordered system. Gravity is the sculptor here, and its strength is directly proportional to mass. The sun's immense gravity creates a deep, smooth well in the fabric of space-time. Picture a vast, taut, elastic sheet of black silk. Now place a heavy, golden sphere in its center. The sphere creates a profound depression. Any smaller marble placed on that sheet will naturally roll down the gentle slopes of that depression, eventually finding a stable path to orbit around the central weight. This is the essence of our solar system's architecture. The planets are not being actively pulled. They are simply following the curved geometry of space that the sun's mass has created. They are in a state of perpetual, graceful freefall around the central gravity well, their forward momentum perfectly balanced against the inward pull. Consider Jupiter for a moment. It is the solar system's planetary heavyweight, more massive than all the other planets combined. Yet, even Jupiter's formidable gravity is utterly subservient to the sun's. Jupiter's path is a gentle, elliptical arc dictated by the sun's dominant presence. The sun's gravity holds sway over distances so vast they numb the mind. It commands the orbit of Neptune, a frigid, blue world so distant that sunlight takes over 4 hours to reach it. It even loosely binds the hypothetical comets of the Oort cloud, almost a light year away, in a grip so tenuous it is like the faintest memory of a touch. This gravitational dominance is not a tyrannical force. It is a nurturing, stabilizing one. It has cleared the solar system's central regions of major debris over billions of years, allowing the planetary orbits to become stable and predictable. This stability is the bedrock upon which the possibility of life was built. A chaotic system with multiple large gravitational competitors would have sent planets on wildly changing paths, leading to catastrophic collisions or ejections into the void. Our sun's quiet, overwhelming dominance provided a calm, constant stage. But the sun's gravity does more than just govern orbits. It shapes the sun itself. It is the force that contains the unimaginable pressures and temperatures of the core, squeezing the hydrogen plasma so tightly that the conditions for nuclear fusion are met. Without this self-gravity, the sun would simply expand and dissipate into space. The outward pressure from the heat of fusion and the inward crush of gravity are in a state of exquisite dynamic equilibrium called hydrostatic balance. This balance is what makes a star a star. For our sun, this balance has held steady for 4.6 billion years, and it will hold for billions more. Each second, millions of tons of mass are converted into energy through fusion, yet the gravitational grip adjusts, keeping the structure intact in a slow, cosmic dance of pressure and containment. There is a beautiful intimacy in this, too. The gravity that holds the planets in their courses is the same force that gives you weight. It is the reason you feel grounded to the Earth. And Earth's gravity, in turn, is a tiny local variation within the Sun's grand field. We are all, always, responding to the Sun's pull. Even when you jump, you are momentarily resisting the combined gravitational influence of the Earth and, ever so faintly, the distant Sun. You are a participant in this gravitational web. So, as you listen, feel the gentle pressure of your body against your bed or chair. That is a local expression of gravity. Now, extend your awareness outward. That same fundamental force, generated by an immense concentration of mass 93 million miles away, is at this very moment guiding our entire world on its annual journey. It is a silent, constant, and benevolent force. It requires no fuel, emits no signal. It simply is a property of mass and space intertwined. The sun does not reach out with grasping hands. It simply rests at the center of its own influence, and the universe around it naturally curves in response. We are not trapped in its orbit. We are dancing with it, partners in a ballet so old and so precise that its rhythms measure the seasons and mark the passage of years. The sun's mass is its quiet command, and our peaceful, predictable journey through the cosmos is its most eloquent testament. From the profound, central anchor of the sun's mass, we now turn our attention to its most beautiful and visible expression, the graceful, perpetual motion it inspires. The sun's powerful gravity is not a chain that binds, but a conductor's hand that guides, orchestrating a silent, slow-motion ballet on a stage nearly empty yet filled with meaning. This is the dance of the solar system, a harmonious interplay of inertia and attraction that has continued for eons. And it is through this dance that we can most viscerally feel the sun's gentle, commanding presence. Imagine once more that deep well in space-time, the gravitational depression created by the sun's mass. Now, picture a single planet like our Earth approaching the rim of this well with a certain sideways momentum. It doesn't fall straight in. Instead, as it slides down the curving slope, its forward motion carries it around the well. It falls forever around the center, never reaching it, its path bending into a closed ellipse. This is an orbit. It is not a forced imprisonment, but a state of perfect, natural balance. A cosmic equilibrium between the desire to fly off in a straight line, inertia, and the pull toward the center, gravity. The sun's gravity provides the central focus, the unwavering point around which all else revolves. Each planet, each asteroid, is finding its own unique balance point on this invisible curved landscape. This results in a symphony of rhythms, each with its own tempo. Mercury, the innermost world, scurries around its fiery host in a mere 88 Earth days, feeling the strongest pull, tracing a tight, fast ellipse. Neptune, the distant blue giant, takes 165 Earth years to complete a single languid circuit, moving with the solemn grace of a giant waltzing in slow motion. These orbital periods, our years, are the direct consequence of their distance from the sun's gravity. Johannes Kepler, centuries ago, heard the music of this system and translated it into laws. Planets sweep out equal areas in equal times, and the square of their orbital period is proportional to the cube of their distance from the Sun. This is not arbitrary law. It is the mathematical signature of the Sun's gravitational influence, a precise formula for the harmony we observe. But the dancers are not just the planets. The asteroid belt, a vast ring of rocky fragments between Mars and Jupiter, is a chorus of countless smaller voices. Here, the Sun's gravity is the organizing principle that prevents these bodies from coalescing into a planet, largely due to Jupiter's disruptive influence, but they still faithfully orbit, a cloud of stone and metal humming along in solar allegiance. Further out, beyond Neptune, the Kuiper Belt hosts icy worlds like Pluto, Haumea, and Makemake, tracing elongated, tilted paths. Their dance is slower, more dreamlike, performed in the faint sunlight of a distant, still commanding star. Then there are the comets, the soloists with the most dramatic performances. They originate in the frozen, dark recesses of the Oort cloud, a spherical shell of icy bodies nearly a light year away. Here, the Sun's gravity is but the faintest whisper, a barely perceptible tug. Yet it is enough. When a subtle nudge, perhaps from the gravity of a passing star, disturbs one of these icy nuclei, it begins a long, slow fall inward. As it plunges down the gravitational slope, it accelerates, swinging around the Sun in a breathtaking close pass. The solar heat vaporizes its ices, creating the magnificent, streaming tails that point away from the Sun's radiation and solar wind. After its dramatic perihelion, it swings back out, returning to the dark, cold depths. Its orbit a long, thin ellipse that speaks of the Sun's far-reaching influence. The gravity that governs the stately planets also whips these icy visitors into fleeting, glorious displays. This gravitational hold also defines the very boundaries of our solar system. The theoretical limit of the Sun's gravitational dominance is the Hill sphere, where its pull is stronger than the tidal forces of the galactic core and nearby stars. This sphere extends perhaps a light year or more. Within this bubble, we are gravitationally the Sun's. Beyond it, we would belong to the galaxy at large. Every object within this sphere, from the pebble-sized meteoroid to the gas giant Jupiter, is, in its heart, attuned to the same central rhythm. Contemplate the peace of this system. There is no friction in the vacuum of space to slow these motions. No grinding of celestial gears. The dance is perpetuated by the initial momentum of the system's birth, conserved and refined over billions of years. It is a clock of unimaginable precision and scale, wound at the dawn of our solar system and still ticking with serene accuracy. The gentle tug you feel keeping you in your seat is a local echo of the same force that keeps Neptune on its multi-decade journey. We are all, from the dust mote to the planet, participants in this grand, slow choreography. So, as you rest, you might envision this, not a static diagram, but a dynamic, flowing masterpiece. A brilliant golden center, and around it swirling, glinting motes tracing ellipses of every size and tilt, some fast, some slow, some in the same plane like stones skipping on a pond, others on steeply inclined paths. It is a mobile of cosmic proportions, moving to the silent music of gravity. There are no collisions, no chaos, only a profound, ordered peace. The Sun does not strain to hold them. Its presence alone creates the conditions for their eternal dance. and we, on our particular mote, are carried along in this flow, experiencing it as the steady cycle of days and years, of seasons returning, of constellations slowly shifting in the night sky. It is the universe's most serene and constant rhythm, a lullaby written in mathematics and motion, playing forever in the quiet theater of space. Now, let us leave the grand, sweeping orbits and come closer to the sun itself. Not to its surface, for it has no surface as we know it, but to its very body. Having felt its mass and witnessed its gravitational poetry, we must now understand its anatomy, its inner architecture. The sun is not a uniform ball of fire. It possesses a deep, layered structure, like the most intricate of Russian nesting dolls or the delicate, concentric rings of a centuries-old tree. Each layer has its own character, its own role in the great work of transforming and releasing energy. Imagine we are on a slow, impossible descent, from the seething heart outward to the wispy, glowing corona, feeling the change in pressure, density, and light as we pass through each serene, spherical shell. Our journey begins at the very center, the core. This is the sanctum sanctorum, the holy of holies, where the magic of nuclear fusion occurs. It is a region extending out to about 1/4 of the sun's radius. Here, conditions are almost beyond imagining. The temperature soars to approximately 15 million degrees Celsius. The pressure is over 250 billion times the atmospheric pressure at sea level on Earth. This immense pressure, generated by the weight of all the overlying layers, squeezes the plasma of hydrogen nuclei, protons, together with incredible force. In this crucible, protons overcome their natural electrical repulsion and fuse, beginning the chain of reactions that turns hydrogen into helium. This is the sun's engine room. Every second, about 600 million tons of hydrogen are fused into about 596 million tons of helium. The missing 4 million tons of mass are converted directly into energy, as per Einstein's E=mc². This energy begins its long, patient journey outward, not as a beam of light, but as extremely high-energy photons of gamma radiation. The core is a place of unimaginable, yet perfectly contained, ferocity, the silent, steady heartbeat of the star. The energy from the core does not rush directly to the surface. It must first pass through the radiative zone. This layer extends from the core's edge to about 70% of the way to the surface. Here, the plasma is still incredibly dense and hot, but not dense enough for fusion. The energy travels through this zone not by fluid motion, but by radiation. A photon of energy is emitted, absorbed by a nearby ion, and then re-emitted. This process happens over and over in a random, zigzagging path. A single photon of gamma radiation generated in the core may take tens of thousands to hundreds of thousands of years to traverse the radiative zone. It is a slow, patient, staggering dance of absorption and re-emission, gradually losing energy and shifting from gamma rays to X-rays and ultraviolet light. Picture this zone as a vast, thick, luminous honey, so dense that light itself must struggle and wander to find a way through. Above the radiative zone lies the convective zone. This is the sun's outer third, extending up to what we perceive as its surface. Here, the plasma is significantly cooler and less dense. It is no longer transparent enough for radiation to be the efficient means of energy transfer. Instead, the energy moves by convection, the same process that heats a pot of soup on a stove. Superheated plasma from the bottom of this zone rises in vast, bubbling cells towards the surface. As it rises, it cools slightly. At the surface, it releases its stored energy as light and heat cools further, becomes denser, and then sinks back down in dark lanes to be reheated, creating a continuous, rolling cycle. This churning motion gives the sun's surface its granular texture, like a pot of simmering golden cereal, with each granule being the size of a continent. This zone is dynamic, turbulent, and is the direct source of much of the sun's magnetic activity. What we see as the sun's surface is the photosphere. This is not a solid boundary, but a thin layer only a few hundred kilometers deep, where the plasma becomes transparent enough for photons to finally escape into space. This is the layer that emits the visible light we see. The temperature here is a cool 5,500 degrees Celsius, which is why the sun appears yellow-white to our eyes. The photosphere is where we observe sunspots, cooler, temporary regions where intense magnetic fields poke through, inhibiting convection. It is the visible skin of our star, the source of the gentle daylight that fills our sky. But the sun's atmosphere extends far above this visible surface. Directly above the photosphere is a thin, reddish layer called the chromosphere, sphere of color. It is about 2,000 to 3,000 kilometers thick and is normally invisible against the photosphere's glare, but can be seen as a pinkish-red rim during a total solar eclipse. Here, temperatures begin to rise again oddly, reaching up to 20,000 degrees Celsius. This is the realm of spicules, dynamic jets of plasma that leap upward like flaming blades of grass. Above that is a very narrow transition region, where temperatures skyrocket from tens of thousands to over 1,000,000 degrees in just a few hundred kilometers. Finally, we reach the outermost layer, the corona. This is the sun's tenuous, superheated outer atmosphere, extending millions of kilometers into space. It is made of incredibly thin, ionized gas glowing at temperatures between 1 and 3 million degrees Celsius, hundreds of times hotter than the photosphere below, a mystery whose solution lies in the sun's magnetic field. The corona is the ethereal, pearly white halo visible during a total solar eclipse, with streamers and loops shaped by magnetic forces. It is from here that the solar wind continuously streams outward, filling the solar system. So, picture the whole, serene structure, a furious creative core, a patient, radiant middle, a churning convective outer layer, a bright, visible surface, and finally, a vast, shimmering million-degree crown that reaches out to touch the planets. It is a symphony in layers, each with its own tempo and instrument, all working in concert to produce the simple, steady glow that greets us each morning. A luminous onion of plasma, whose center is a relentless forge and whose outermost breath is the gentle solar wind that caresses our world. We have mapped the sun's serene anatomy, from its million-degree corona down to its continent-sized granules. Now we descend to the very source of it all, to the quiet, relentless miracle at its heart. We have spoken of the core as an engine room, a forge, but these are mechanical terms. What happens there is something far more elegant, a fundamental process that stitches the fabric of the universe itself. Nuclear fusion. This is the sun's silent, persistent roar, the alchemy that transforms mere substance into light and warmth, and has done so for nearly 5 billion years without fail. Let us explore this process not as a violent explosion, but as a gentle, continuous creation, the universe's way of making sunlight. The core's environment, as we've felt, is one of unimaginable pressure and heat. Here, hydrogen nuclei, which are simply single protons, are moving at tremendous speeds. Normally, two positively charged protons repel each other fiercely due to the electromagnetic force. Think of trying to push the same poles of two powerful magnets together. They resist. But in the sun's core, the conditions are so extreme that this natural repulsion is overcome. The protons are moving so fast, a result of the extreme temperature, and are squeezed so close together, a result of the extreme pressure, that they can come within an infinitesimally small range of a different, much stronger force, the strong nuclear force. This force only acts at subatomic distances, but when it engages, it can bind protons together, overcoming their electrical aversion. The process of turning hydrogen into helium is not a single step, but a delicate, multi-stage dance known as the proton-proton chain. It begins with two protons colliding and fusing. One of them undergoes a transformation, turning into a neutron through the release of a positron, a positively charged electron, and a nearly massless particle called a neutrino. This new proton-neutron pair forms a nucleus of deuterium, which is a heavy form of hydrogen. The released neutrino escapes the sun almost immediately, ghost-like, passing through the entire star and out into space, barely interacting with anything. Trillions of them are passing through your body every second, a silent rain from the heart of the sun. This deuterium nucleus then collides with another proton. They fuse, forming a light isotope of helium, helium-3, and releasing a burst of gamma-ray energy. Finally, two of these helium-3 nuclei meet and fuse, creating a stable nucleus of regular helium. 4, 2 protons, 2 neutrons, and releasing 2 spare protons back into the plasma soup to start the process again. It is a cyclical, self-sustaining reaction. The net result, as we heard before, 4 hydrogen nuclei are fused into 1 helium nucleus. But in that transformation, a tiny fraction of the original mass, about 0.7%, does not survive as matter. It is converted purely into energy in accordance with Einstein's famous equation, E equals mc squared. The c in that equation is the speed of light, an enormous number, and squaring it makes it astronomically larger. This is why a tiny loss of mass results in a colossal release of energy. The sun converts over 4 million tons of matter into energy every second. This number feels immense, yet remember the sun's scale. It is a gentle, measured burn, not a detonation. This energy first manifests as high-energy gamma-ray photons. They begin their epic journey outward, as we've learned, through the radiative and convective zones, slowly losing energy, morphing into the visible light and warmth we know. The fusion process is exquisitely self-regulating. It is a perfect balance. The gravitational force of the sun's immense mass constantly pulls inward, compressing and heating the core. This heat and pressure drive the fusion reactions faster. The energy released by fusion creates an outward pressure that pushes against the crush of gravity. If fusion were to momentarily spike, the increased outward pressure would slightly expand the core, cooling it and slowing the fusion rate back down. If fusion waned, gravity would compress the core, heating it and speeding fusion up again. This feedback loop, hydrostatic equilibrium, is the reason our sun burns so steadily. It is a stellar thermostat set for billions of years of gentle, consistent output. Contemplate the depth of time here. The light warming your skin today was generated by a fusion event that occurred hundreds of thousands of years ago in the core, taking that long to wander to the surface. The neutrino that slipped through your hand a moment ago was created just over 8 minutes ago, traveling at nearly the speed of light from the core to you in a straight shot. We are connected to the sun's deep past and its present heart simultaneously. This process is the ultimate recycling. The hydrogen fuel is the primordial ash of the Big Bang. The helium produced is a new element stored in the core. Over the eons, the core becomes enriched with this helium ash. For now and for billions of years to come, the proton-proton chain will dominate. But this gentle beginning contains the seed of the sun's eventual end. One day, the hydrogen in the core will begin to run low. That distant future is written in the physics of this very reaction we're describing now. For now, though, let us simply marvel at the quiet reliability of it. In the absolute darkness and cold of space, a sphere of gas, governed by nothing but gravity and quantum mechanics, has sustained a tiny, contained point of nuclear fire. It does not rage. It simmers. It is not a bomb. It is a hearth. Every ray of sunshine, every glint of light on water, every shadow cast by a leaf is the direct, multimillennial descendant of a pair of protons overcoming their fear of each other in the heart of a star, embracing under pressure to create something new, and in doing so, gifting the universe with light. It is a story of transformation and constancy, written in the language of atomic nuclei and played out on a stage of cosmic scale. And it is happening right now, as you listen 93 million miles away, a silent, everlasting forge weaving sunlight out of stardust. From the silent, transformative forge of the core, let us now follow the energy's path outward and consider the element that defines every layer of the sun's being: temperature. We have heard the numbers 15 million degrees in the core, 5,500 degrees at the visible surface, but these are more than statistics. They are signatures of different states of matter and energy, a gradient of heat that tells the story of the sun's structure and stability. To understand the sun is to feel this gradient, not as a threat, but as a natural, majestic spectrum of thermal existence, from the unimaginably fierce to the familiarly warm. We begin once more at the heart, 15 million degrees Celsius. This is the thermal floor of our star's engine. At this temperature, matter as we know it ceases to exist. Atoms are completely ionized. Electrons are stripped from nuclei, creating that seething plasma of bare protons, helium nuclei, and free-flying electrons. This heat is not a burning chemical fire. It is the heat of particle speed, of violent, relentless motion. It is the kinetic energy required to force positively charged protons together against their powerful mutual repulsion. This number, 15 million, is the minimum threshold for the proton-proton chain to ignite and sustain itself. It is the temperature of creation, where mass is transmuted into energy. Picture it not as a destructive inferno, but as the necessary warmth of a cosmic womb, where elemental alchemy occurs. As energy travels outward through the radiative zone, the temperature gradually decreases. By the time we reach the base of the convective zone, about 70% of the way from the core to the surface, temperatures have fallen to around 2 million degrees Celsius. It is still blisteringly hot by any human measure, Yet it is here that the plasma becomes just cool and dense enough for convection to begin. The change in heat transfer method is a direct consequence of this cooling. The plasma can no longer remain transparent enough for radiation to be efficient, so it must move, carrying heat in great bubbling cells. Then we arrive at the photosphere, the sun's visible surface. Here, the temperature is a comparatively gentle 5,500 degrees Celsius, about 9,900 degrees Fahrenheit. This is the temperature of the light that reaches our eyes. It is crucial to understanding why the sun appears the color it does. We often think of the sun as yellow. In space, it is actually white. Our atmosphere scatters the shorter, bluer wavelengths of light, leaving the longer, redder and yellower wavelengths to dominate the direct beam. Hence the golden hue at sunrise and sunset and the yellowish-white disk at noon. This 5,500 degree temperature defines it as a G-type main sequence star, or a yellow dwarf. This surface temperature is a key part of the sun's identity, placing it in a stable, middle-of-the-road category of stars, not as hot and blue as an O-type giant, nor as cool and red as an M-type dwarf. But the story of solar temperature holds one of its most intriguing mysteries. As we move above the visible surface into the atmosphere, intuition would suggest the temperature should continue to drop, like the air thinning and cooling as you climb a mountain on Earth. Instead, the opposite occurs. In the thin chromosphere, temperatures rise again to between 10,000 and 20,000 degrees Celsius. And then, in the transition region and the corona, they skyrocket to 1 to 3 million degrees Celsius, hundreds of times hotter than the photosphere below. How can the tenuous outer atmosphere be vastly hotter than the surface that heats it? This is the coronal heating problem, one of the great puzzles in solar physics. The leading theory points to the sun's powerful and dynamic magnetic field. It is thought that magnetic energy, generated by the churning motion of the convective zone, is continuously released in the corona through a process called nanoflare heating or via magnetic waves. It's as if the sun's visible surface is a warm stove, but just above it, an invisible field of energy cooks the thin air to temperatures far exceeding the stove's surface. This million-degree corona is the source of the solar wind, that gentle breeze of charged particles that flows past Earth. Let's bring this thermal gradient home. The warmth you feel on your skin on a sunny day is energy from the 5,500-degree photosphere, filtered through 93 million miles of space and our protective atmosphere. It is diluted, softened, rendered benign and life-giving. The sun's output is so constant that we call it the solar constant, about 1,361 watts of power per square meter at Earth's distance. This constancy is a gift of its stable core temperature and the exquisite balance of hydrostatic equilibrium. Even the sunspots, those temporary blemishes on the photosphere, are only cool in relative terms, about 3,500 degrees Celsius compared to the surrounding 5,500. They are still incandescently hot, appearing dark only by contrast. Contemplate this range. From the core's 15 million degrees to the photosphere's 5,500, to the corona's renewed millions. It is a testament to the sun's layered, complex nature. Each temperature defines a role, a state of matter, a method of energy transport. The core's extreme heat enables fusion. The photosphere's moderate heat emits the visible light we see. The corona's mysterious heat accelerates the solar wind that creates the auroras. This thermal architecture is not chaotic. It is a stable, self-regulating system. The sun is not simply hot. It is a carefully graded symphony of heat, each note essential to the whole. As you relax, perhaps feeling the residual warmth of the day in your room or the coolness of the night, remember that the concept of temperature itself is a spectrum of motion. The comfort you feel is a direct, distant cousin to the frenzy in the solar core. Both are expressions of particles in motion, one life-destroying, the other life-sustaining, bridged by the vast, peaceful distance of space and the gentle filters of physics. The sun maintains its fiery heart so that we, on our tiny orbiting world, can experience its energy as a caress, not a conflagration. Its temperature is not a single note, but a chord deep, complex, and ultimately perfectly tuned to allow a world like ours to exist in its gentle golden glow. Having journeyed through the sun's thermal landscape, from its fervent core to its mysteriously hot corona, let us now turn our attention to a more subtle, yet profoundly important aspect of its being, its motion. We have seen how it anchors the solar system with its gravity and how it burns with a steady heart. But the sun itself is not static. It spins, it rotates, yet this is not the simple, solid turning of a globe on a desk. The sun's rotation is a fluid, graceful, and complex phenomenon, a key that winds the clock of its magnetic heart and reveals its true nature as a ball of plasma. Let us explore this slow, differential whirl, a cosmic waltz that shapes the star's very soul. If you could float in space and watch the sun for a period of days, you would notice a slow but definite movement. Sunspots, those temporary freckles on the photosphere, drift steadily across the face of the disk, disappearing over the western limb and, if they are long-lived, reappearing on the eastern limb about 2 weeks later. This is our visual proof of the sun's rotation. But when astronomers first measured this motion by tracking sunspots centuries ago, they encountered a puzzle. The rotation period they calculated depended on where on the sun they looked. The sun, it turns out, does not rotate as a rigid body. It spins differentially. This means the equatorial regions rotate faster than the polar regions. At the sun's equator, it takes approximately 25 Earth days to complete one full rotation. At higher latitudes, closer to the poles, the rotation slows. It takes about 35 Earth days for the polar regions to complete a single turn. Imagine a ball of honey or a very viscous fluid, where the middle spins freely while the top and bottom drag. The sun, as a massive sphere of superheated plasma, behaves like a fluid. There is no solid crust to enforce a single rotational speed. This differential rotation is a fundamental consequence of its gaseous state and has deep implications. To visualize this, picture the sun not as a perfect sphere, but as a vast, gentle whirlpool of light. The material at its equator is tracing a much larger circle than the material near the poles. To complete its circuit in roughly the same time frame, the equatorial plasma must move faster. This creates a shearing effect, where different layers and latitudes slide past one another. This slow, relentless shear is one of the primary engines for the sun's powerful and complex magnetic field. It twists and stretches the magnetic field lines that are rooted in the convective zone below, like taffy being pulled, storing immense amounts of energy that will later be released as solar activity. This rotation also means there is no single solar day as we have on Earth. A day on the sun is a fluid concept, stretching from 25 days at the equator to over a month at the poles. For an observer hypothetically standing on the sun's surface, an impossible feat. The passage of day into night would be an achingly slow, weeks-long process, the Terminator line creeping across a landscape of seething plasma granules. The rotation axis of the Sun is tilted by about 7.25 degrees relative to the plane of the solar system, the ecliptic. This is a slight tilt, not enough to give it pronounced seasons as on Earth, but it does mean that from our perspective on Earth, we see slightly more of the Sun's northern polar region in September and more of its southern polar region in March. How do we know the rotation continues deep inside? Helioseismology, the study of solar oscillations, allows us to listen to the Sun. The churning convection creates sound waves that travel through the solar interior. By studying these global vibrations, much like geologists study seismic waves to understand Earth's interior, scientists can map the rotation profile deep within. They find that the differential rotation pattern persists through the convective zone. However, beneath that, in the radiative zone and the core, the Sun appears to rotate more like a solid body, all parts turning together once every about 27 days. This creates a fascinating boundary layer between the differentially spinning convective zone and the uniformly rotating interior, a region of intense shear that further influences magnetic field generation. This constant differential spin is the heartbeat of the Sun's magnetic cycle. Over a period of about 11 years, the Sun's magnetic field flips polarity. North becomes south and vice versa. This cycle is intimately tied to the winding up of magnetic field lines by the differential rotation. Think of it as a slow cosmic dynamo. The shearing motion stretches and wraps the magnetic fields, increasing their tension until they become unstable. They then buoyantly rise through the convective zone and erupt through the photosphere as sunspot pairs or release their energy in flares and coronal mass ejections. The 25-day equatorial rotation sets the pace for this winding, making the magnetic cycle a direct child of the Sun's spin. As you rest, consider this gentle motion. Our seemingly constant, unchanging Sun is in a state of perpetual, graceful turn. It is a dancer, but a dancer whose skirt swirls at a different pace at the hem than at the waist. This motion is not frantic. It is stately, immense, and slow. A single day at the Sun's equator lasts longer than most of our months. This slowness is a comfort. It speaks of stability, of a rhythm measured in weeks, not seconds. We on Earth are carried along by this rotating star. Our entire frame of reference, the east-to-west journey of the Sun across our sky, is a reflection of our own planet's spin, but we are orbiting a center that itself is turning. Everything is in motion, yet from our vantage point, it creates the perfect illusion of constancy. The Sun rises and sets with such reliability that we build our lives upon it. We are soothed by its predictability, unaware of the complex, shearing whirl at its heart that makes such constancy possible. It is a beautiful paradox. The Sun's differential rotation, a source of dynamic magnetic storms, is also part of the engine that guarantees its long-term, steady glow. A fluid turn in the void, weaving invisible fields of force, all to produce the simple, familiar arc of daylight we know and love. A slow spin, a deep breath, a celestial clock wound by the laws of fluid dynamics, ticking away the peaceful epochs of our solar system. From the deep, fluid whirl of the Sun's differential rotation, we now turn our gaze to an invisible architecture that this motion helps to create. an architecture of force and influence that shapes the sun's most dramatic features and reaches out across the solar system to touch our own world in subtle and beautiful ways. This is the realm of the sun's magnetic field. Invisible to the eye, it is the great sculptor of solar activity, the artist behind the sunspots, the driver of solar storms, and the weaver of the magnificent shimmering corona. To understand the sun's dynamic personality, we must learn to sense this hidden field of force, not as a source of danger, but as a natural expression of its churning plasma heart. The sun's magnetic field is generated by a process known as a dynamo. This dynamo is powered by the combination of two things: the convective motion of the plasma in the outer third of the sun and the differential rotation we just explored. Imagine the sun's interior as a vast, turbulent ocean of electrically conductive fluid, the plasma. As this plasma churns and rises and falls in the convective zone, it carries with it any weak, pre-existing magnetic fields. The differential rotation, the faster spin at the equator than at the poles, then stretches and wraps these magnetic field lines, like taffy being spun and twisted. This process amplifies the magnetic field, transforming the kinetic energy of motion into magnetic energy. Over time, these wound-up magnetic field lines become incredibly tense and complex, forming ropes and loops that can burst through the sun's visible surface. Where these intense, knotted bundles of magnetic field lines erupt through the photosphere, they create the most recognizable magnetic feature: sunspots. A sunspot is not a hole or a blemish, but a region where the magnetic field is so strong, thousands of times stronger than Earth's magnetic field, that it suppresses the normal convective heat flow from below. The plasma within the sunspot is cooler than the surrounding photosphere, hence it appears dark, but only by contrast. It is still brilliantly hot at around 3,500 degrees Celsius. Sunspots often appear in pairs or groups with opposite magnetic polarity, like the two ends of a submerged U-shaped magnet. Their ebb and flow over an approximately 11-year cycle is the most visible heartbeat of the solar dynamo, marking periods of high and low magnetic activity. But the magnetic field's influence extends far beyond these temporary cooler patches. It structures the sun's entire outer atmosphere. In the corona, the magnetic field loops and arches, tracing graceful paths for the superheated plasma. These are the coronal loops, glowing brilliantly in ultraviolet and X-ray light, holding plasma aloft in magnificent, slow-motion arcs that can be many times the size of Earth. The magnetic field is also responsible for confining and shaping the prominences, huge, glowing clouds of cooler plasma that hang suspended above the solar surface, often for weeks, tracing the lines of magnetic force like dew on a cosmic spiderweb. When viewed against the dark backdrop of space at the sun's limb, they appear as luminous, pinkish filaments or towering arches. However, this magnetic architecture is not always stable. The constant churning and twisting can cause magnetic field lines to become too strained, to cross, or to suddenly reconfigure, a process called magnetic reconnection. This is the trigger for the sun's most energetic releases. In a fraction of a second, the pent-up magnetic energy is converted into intense radiation, particle acceleration, and plasma heating. We see these events as solar flares, sudden, brilliant flashes of light across the electromagnetic spectrum, from radio waves to gamma rays. A major flare can release energy equivalent to billions of atomic bombs, yet it is a localized event on the sun's vast face, a brief, intense spark in the magnetic tapestry. Sometimes the reconnection event is so powerful it doesn't just release radiation, but also hurls a massive parcel of the corona's magnetic field and plasma out into space. This is a coronal mass ejection, or CME. A CME is a billion-ton cloud of charged particles traveling at millions of miles per hour. It is the solar system's largest explosive event. When directed toward Earth, this magnetized cloud can interact with our planet's own magnetic field, compressing it and triggering geomagnetic storms. This is where the sun's hidden magnetic force touches our lives' invisible poetry. The energetic particles from the solar wind and CMEs are funneled by Earth's magnetic field down toward the polar regions. There, they collide with atoms in our upper atmosphere, exciting them and causing them to glow. This is the aurora, the northern and southern lights. The shimmering curtains of green, red, and purple are a direct, beautiful conversation between the sun's magnetic fury and Earth's magnetic shield. It is a reminder that we live within the sun's extended atmosphere, its magnetic influence a constant, gentle presence. The sun's global magnetic field is also fluid. Every 11 years, at the peak of the sunspot cycle, the entire magnetic field of the sun flips polarity. The north and south magnetic poles swap places. This is part of a 22-year magnetic cycle, where the field returns to its original orientation after two 11-year sunspot cycles. This grand, slow reversal is the ultimate expression of the solar dynamo at work, a deep, rhythmic pulse in the life of our star. So, as you relax, envision the sun not just as a source of light, but as a source of invisible lines of force. Picture them emerging from its interior, weaving a complex, ever-changing web across its surface and filling its atmosphere with glowing loops and filaments. These lines are the reins that guide the solar wind and the framework upon which solar storms are built. They are powerful, yet they follow the elegant laws of magnetohydrodynamics. This magnetic personality makes the sun a living, breathing entity, not a static lamp. Its occasional flares and ejections are not signs of anger, but of vitality, the natural sighs and exhalations of a dynamic star. And from our safe distance, we can appreciate these phenomena as a distant, magnificent spectacle, the source of our protective magnetic shield and the painter of our polar skies. The same force that creates the dark, Earth-sized spots on its face also creates the ethereal lights that dance in our own night. It is all connected, a single beautiful system of plasma, motion, and magnetism humming quietly in the void. In the silent, magnetic tapestry of the sun, there is a rhythm, a slow, deep pulse that governs its activity, a cycle of rest and awakening that unfolds not over days or seasons, but over years. We have felt the presence of sunspots, those temporary islands of concentrated magnetism. But they do not appear at random. They come and go in a grand, predictable wave, a cycle that has repeated itself like clockwork for centuries. This is the solar cycle, an approximately 11-year heartbeat that reveals the sun not as a static beacon, but as a living, breathing entity with seasons of its own. Let us attune ourselves to this slow rhythm, a rhythm so gradual we can only perceive it through patient observation over decades. The most visible marker of this cycle is the number of sunspots on the sun's face. At the cycle's beginning, a period called solar minimum, the sun can appear utterly blank for weeks or even months, a flawless, quiet disk of light. Then, almost shyly, the first spots begin to appear. Not at the equator, but at mid-latitudes, around 30 degrees north and south. They are small, often solitary. As the years progress, the spots grow more numerous, larger, and more complex. They also begin to appear closer and closer to the solar equator. This activity peaks at solar maximum, when the sun's face can be dotted with many groups of spots, some far larger than our planet. After this crescendo, the numbers begin to dwindle, the spots retreating again toward the equator until they fade away, and the sun returns to its quiet, spotless state. This entire journey from minimum to maximum and back to minimum takes about 11 years on average, though individual cycles can vary from 9 to 14 years. This migration of sunspot latitudes creates a beautiful pattern when charted over time. If you plot the latitude of sunspots against the year, a shape emerges resembling a series of staggered butterfly wings, a pattern astronomers call the butterfly diagram. It is a visual testament to the cycle's ordered progression, a slow wing beat of magnetic activity drifting from the sun's mid-latitudes toward its waist. But the solar cycle is about far more than just sunspots. It is the cycle of the sun's global magnetic field. At solar minimum, the sun's magnetic field is relatively simple and stable, resembling that of a large, slightly tilted bar magnet with clear north and south poles. As differential rotation winds up the magnetic field lines from the interior, the field grows complex and stressed. Sunspots are the visible signatures of this stressed magnetic field punching through the surface. The true climax of the cycle is not just the peak in sunspot number, but the moment of polarity reversal. Around the time of solar maximum, the sun's entire global magnetic field flips. The north magnetic pole becomes the south and vice versa. This reversal doesn't happen instantly. It is a gradual, messy process over many months where the polar fields weaken, drop to zero, and then rebuild with the opposite polarity. This means the complete magnetic cycle from one polarity through a reversal and back to the original polarity is actually about 22 years long. This magnetic upheaval drives all other forms of solar activity. Solar flares, those sudden flashes of radiation, are much more frequent during solar maximum. The massive coronal mass ejections, CMEs, that can send billion-ton clouds of plasma hurtling into space are also more common. Even the sun's steady output of extreme ultraviolet and X-ray light varies with the cycle, being significantly higher at maximum. This variation, though a tiny fraction of the sun's total visible light output, has a profound effect on the upper layers of Earth's atmosphere, causing it to expand and contract slightly over the cycle. Why does this cycle exist? It is the natural outcome of the solar dynamo we discussed, the interplay between differential rotation, which stretches the magnetic field, and convection, which twists and buoyantly lifts it. Think of it as a slow-motion engine. The differential rotation winds the magnetic field like a spring, storing energy. Eventually, the wound-up magnetic fields become buoyant and rise through the convective zone to erupt as sunspots and active regions, releasing energy. After the reversal, the new, simplified magnetic field begins the process of being wound up again, but with its polarity opposite. It is a self-regulating, oscillating system, a fundamental mode of the sun's dynamo. For us on Earth, this cycle is a background whisper in the natural world. During solar maximum, the increased frequency of geomagnetic storms means auroras are more likely to be seen at lower latitudes, sometimes painting the skies over places like Scotland, or the northern United States with shimmering colors. The enhanced solar wind can also slightly increase drag on satellites in low Earth orbit, and the stronger radiation environment poses a marginally higher risk to astronauts and spacecraft electronics. Yet, these effects are gentle ripples from a distant storm. The sun's total light output, the solar constant, varies by only about 0.1% over the cycle, a testament to the stability of its core fusion engine. The cycle affects the sun's magnetic personality, not its fundamental warmth. As you drift, consider this immense, patient rhythm, an 11-year pulse. While our lives rush forward in a blur of days and months, the sun is marking time in units longer than a decade. Civilizations have risen and fallen within a single solar cycle, unaware of the slow dance of magnetism on the star that sustained them. It is a rhythm that connects us to the long-term life of our star, a reminder that constancy is not the same as stillness. The sun is constant in its light, but dynamic in its spirit. Its cycle is like a slow, deep breath, a years-long inhalation of gathering magnetic energy, and an exhalation of release and reversal. We are living within one of its breaths right now, and as we listen to its story, we can feel a sense of peace in this grand, predictable tempo, a rhythm that links the sunspot you might have seen through a telescope once to the ancient observations of Chinese astronomers and to the satellite data of today, all tracing the same serene celestial heartbeat. We have felt the sun's magnetic heartbeat and witnessed its cyclic breath through sunspots and flares. Now, let us follow the gentlest, most persistent of its exhalations, one that flows not in bursts, but in a perpetual silent stream. This is the solar wind, an ethereal breeze of charged particles that flows outward from the sun in all directions, filling the solar system and defining the very bubble in which we live. It is an invisible river, carrying with it the sun's magnetic fingerprint and sculpting the environment of every planet it passes. To understand our place in space is to feel this constant, soothing wind on the face of our world's magnetic shield. The story of the solar wind begins in the sun's million-degree corona. We've learned that the corona is mysteriously hot, far hotter than the visible surface below. This intense heat gives the particles in the corona, mostly electrons and protons, the stripped nuclei of hydrogen atoms, tremendous kinetic energy. At these temperatures, the particles are moving so fast that the sun's immense gravity cannot hold onto them all, especially in the outer, less dense regions of the corona. They achieve what is called escape velocity. Like steam rising from a hot cup of tea, these charged particles stream away from the sun, accelerated further by the pressure of the magnetic fields in the corona. This is not an explosion, but a continual, gentle evaporation of the sun's outermost atmosphere into the void. This wind is not uniform, comes in two primary streams. The fast solar wind gusts at speeds of about 750 to 800 kilometers per second, nearly 2 million miles per hour. It originates from areas in the corona known as coronal holes, vast, dark regions seen in ultraviolet light where the sun's magnetic field lines open out into space, allowing the plasma to flow freely unimpeded by looping magnetic structures. The slow solar wind, traveling at a more leisurely 300 to 400 kilometers per second, emanates from above the more complex, magnetically active regions around the sun's equator. Together, they create a variegated flow, a cosmic weather pattern that changes with the solar cycle. As this wind streams outward, it does not travel into nothingness. It creates something magnificent, the heliosphere. Imagine the solar wind as an exhaled breath that pushes against the thin, tenuous gas and dust that fills the space between stars, the interstellar medium. The heliosphere is the vast, teardrop-shaped bubble formed by this pressure balance, where the solar wind's outward push dominates over the inward pressure of the galactic environment. Within this bubble, we are truly in the sun's domain. Every planet, every comet, every asteroid orbits within the sun's extended atmospheric breath. The boundary of this bubble is not a sharp wall, but a series of transitional regions. Far, far out, about 80 to 100 times the distance from the Earth to the Sun, the solar wind, having traveled for nearly a year, begins to slow down as it starts to press against the interstellar medium. This region is called the termination shock. Here, the wind abruptly decelerates from supersonic to subsonic speeds, becoming denser and hotter. Beyond that lies the heliosheath, a turbulent, thicker region where the slowed solar wind piles up and churns, deflected by the interstellar flow. The true outer edge of the heliosphere is the heliopause. This is the theoretical surface where the pressure of the solar wind finally balances exactly with the pressure of the interstellar medium. It is the shoreline between our solar system and the galaxy proper. In 2012, the Voyager 1 spacecraft, a tiny human-made artifact launched in 1977, crossed this frontier, becoming the first object to enter interstellar space. Its instruments sensed a dramatic drop in solar wind particles and an increase in galactic cosmic rays. It confirmed that we live in a protective, sun-blown bubble. But the sun is moving. As it orbits the galactic center, it plows through the local interstellar cloud. This motion creates a sort of bow wave ahead of the heliosphere called the bow shock or heliospheric bow wave, much like the wave that forms ahead of a boat moving through water. Meanwhile, behind the sun, the heliosphere stretches out into a long, streaming heliotail, likely divided into distinct lobes by the solar magnetic field. Our entire solar system, then, resembles a great ship sailing through the galactic sea, its solar wind carving a protective cocoon around it. This constant, invisible wind has gentle, tangible effects on our home. The solar wind carries with it the sun's interplanetary magnetic field, a spiraling pattern often called the Parker spiral, wound by the sun's rotation, like water from a spinning garden hose. When this magnetized wind encounters Earth's own magnetic field, it interacts. Most of it is deflected by our magnetosphere, a protective magnetic shield. But some particles are funneled down the magnetic field lines toward the poles, where they create the aurora borealis and australis. The solar wind is the painter of those ethereal lights. It also shapes the tails of comets. As a comet's ices vaporize near the sun, the solar wind and radiation pressure push that gas and dust into the iconic, streaming tails that always point away from the sun. The solar wind even helps erode the atmospheres of planets that lack strong magnetic fields, like Mars, slowly stripping them away over eons. So, as you rest, envision this serene, endless flow. From the sun's shimmering corona, a breeze of charged particles slips away, accelerating into a silent gale that fills the space between worlds. It is a wind that takes nearly a year to reach the bubble's edge, a wind that has blown for billions of years. We are immersed in it. It is a physical connection, a constant, gentle pressure from our star. While we feel the sun's light on our skin, our planet feels its wind on its magnetic face. This wind is the sun's way of touching the outer planets, of communicating with the galaxy, of declaring its presence in the interstellar dark. It is a whisper that becomes a shield, a breath that becomes a boundary. And within that breath, we live, protected and connected, sailing on a ship of light through the cosmic ocean, forever accompanied by the gentle, unfailing exhalation of our star. After floating on the serene, perpetual currents of the solar wind, we now turn to moments when the sun's dynamic nature expresses itself not as a steady breeze, but in sudden, magnificent sighs of release. These are the solar system's most powerful transient events: solar flares and coronal mass ejections. To our ancestors, they were invisible, their effects perhaps only guessed at through the rare, storm-lit auroras seen at unlikely latitudes. To us, with our electronic eyes in space, they are breathtaking displays of cosmic power. Yet, even in their violence, there is a profound order and beauty. Let us understand these events not as the sun's anger, but as its natural exhalations, necessary releases of pent-up magnetic energy that remind us we orbit a living star. First, let us distinguish between the two, for they are related but different phenomena. A solar flare is a sudden, intense flash of light, a brilliant increase in brightness that occurs near the sun's surface, usually above a complex group of sunspots. It is a local event, a torrent of radiation across the entire electromagnetic spectrum, from radio waves to visible light to X-rays and gamma rays. Think of it as a flash of lightning within the sun's atmosphere, a brief but ferocious spark of light. In mere minutes, a large flare can release energy equivalent to billions of megatons of TNT. Yet this energy is spread across a vast area and a broad spectrum. A coronal mass ejection, CME, on the other hand, is a much more massive, slower, and tangible event. It is the eruption of the sun's very substance. Imagine a vast, billion-ton cloud of the corona's superheated plasma, protons, electrons, and embedded magnetic fields, being violently hurled out into space. While flares are flashes of light, CMEs are actual projectiles of matter. They can occur alongside powerful flares, but they are distinct. A CME can take hours to fully erupt and then days to travel across the space between the sun and Earth. It is the solar system's largest form of weather, a storm front of magnetized gas. The root cause of both lies in the sun's magnetic field. In the intense magnetic tangles above sunspot groups, field lines become twisted, stretched, and stressed by the motion of the plasma below. Oppositely directed magnetic field lines can be pushed together. When they meet, they can suddenly reconnect. This process of magnetic reconnection is like cutting two taut, twisted rubber bands and letting them snap into a new, simpler configuration. In that snapping, the immense magnetic energy stored in the twists is converted explosively into heat, particle acceleration, and light, a flare. Sometimes the reconfiguration is so drastic it blasts open a magnetic structure, propelling a vast loop of plasma and field outward, a CME. The scale of these events is humbling. A large CME can contain a mass equivalent to a small mountain, racing outward at speeds ranging from 250 kilometers per second to over 3,000 kilometers per second for the most extreme events. As it expands, it can become larger than the sun itself, a colossal bubble that, if directed toward us, will wash over our entire planet. When such a directed cloud, a halo CME, arrives at Earth, it interacts with our planet's magnetic shield, the magnetosphere. The impact compresses the dayside magnetosphere and can trigger a geomagnetic storm. This is where the sun's distant fury translates into effects we can observe and occasionally feel. The most beautiful effect is the aurora. A strong geomagnetic storm can push the auroral oval far from the poles, allowing people in temperate latitudes like Europe, the northern United States, or southern Australia to witness the shimmering curtains of green, red, and purple. It is the sun's most direct and gorgeous artwork on our earthly canvas. But these storms also have more practical effects. The rapid changes in the Earth's magnetic field can induce powerful electrical currents in long conductors on the ground, like pipelines, railways, and, most significantly, power grids. The most famous example is the Carrington event of 1859, a solar superstorm that caused telegraph systems worldwide to fail, with operators receiving shocks and papers catching fire from the induced currents. In our vastly more electrified and technologically dependent world, a similar event today could cause widespread, prolonged power blackouts and damage satellites. The energetic particles can also pose a radiation hazard to astronauts in space and to passengers and crew on high-altitude polar flights. Yet, it is crucial to hold this in perspective. Such extreme events are rare. Our sun, for the most part, is a gentle neighbor. Its flares and CMEs are part of its natural cycle, peaking every 11 years. Our modern technology allows us to monitor these storms from satellites like SOHO and ACE, giving us precious hours or days of warning to protect vulnerable infrastructure. It is a testament to our growing harmony with our stars' rhythms. So, as you listen, picture these events in their full, distant majesty. See the flare, a brilliant, localized flash on the sun's limb, a silent detonation of light that travels to us in just over 8 minutes. See the CME, a graceful, blooming halo of incandescent plasma, slowly billowing outward like a cosmic flower opening in the void. They are not signs of a malevolent star, but of a dynamic, magnetically active one. They are the sun's way of shedding excess energy, of untangling its twisted magnetic fields. They remind us that we live in the atmosphere of a star, subject to its weather. But just as we are prepared for a thunderstorm on Earth, we are learning to live with the storms from our sun. They are part of the relationship, the breathtaking, powerful, and ultimately life-enriching dialogue between our world and its fiery heart. The same magnetic forces that can disrupt our technology also create the protective magnetosphere that shields us from the harsher cosmic rays and paint our skies with the otherworldly beauty of the aurora. It is all one interconnected system, singing a song of plasma and magnetism, of calm winds and occasional, magnificent storms. Following the grand, stormy size of flares and coronal mass ejections, let us return to the most constant and gentle of the sun's gifts, its light. And not just the fact of it, but the journey of it. Every beam of sunshine that warms your skin, every glint you see on water, is a traveler with a story. It began a journey over 8 minutes ago, covering a distance of 93 million miles at the universe's ultimate speed limit, only to arrive here, now, in this quiet moment. Alongside this light travels another, invisible messenger, the solar wind. Together, they engage in a silent, beautiful dialogue with our world. A dialogue whose most visible line is written in shimmering color across the polar night. Let us trace this dual journey from the sun's surface to our senses. First, the light. The photons that constitute sunlight are born in the photosphere, the sun's visible surface. Each one is emitted from a seething, churning granule of plasma as it cools slightly after rising from the convective depths. Once free, these photons rush outward into space in every direction, unimpeded. They travel at light speed, 186,282 miles per second, a staggering velocity, yet space is vast. The distance between the Sun and Earth is, on average, about 93 million miles, 150 million kilometers. To bridge that gulf, light takes approximately 8 minutes and 20 seconds. Pause on that number. It is a bridge between now and then, between here and there. The sunlight you see is not the sun as it is in this instant, but as it was over 8 minutes ago. When you look at the sunset, you are seeing the sun's face from 8 minutes in the past. This delay is our cosmic cushion, a slight buffer of time and space. It also means we always experience the sun with a gentle latency. If the sun were to somehow vanish this very second, we on Earth would continue to see its light, feel its warmth, and orbit its now empty point in space for 8 more minutes, blissfully unaware. It is a poignant reminder of our separation and our connection. While light brings us the sun's image and warmth, the solar wind brings its substance and magnetic influence. This stream of charged particles, flowing at a comparatively glacial pace of a few hundred kilometers per second, takes not minutes, but typically 1 to 3 days to voyage from the sun to Earth. So, when a particularly strong gust from a coronal hole arrives, or when the leading shock wave of a coronal mass ejection strikes, we are feeling an event that occurred days earlier on the sun. We live in a delayed reality, with light as our speedy news service and the solar wind as the slower, tangible freight. Now, picture these two travelers arriving at our blue world. The light passes through our atmosphere, scattering to create our blue sky, bathing the dayside in illumination. The solar wind, however, meets a barrier, Earth's magnetosphere. This is a protective bubble generated by our planet's rotating, molten iron core, a magnetic field that extends tens of thousands of kilometers into space. For the most part, this shield deflects the solar wind, carving out a protected cavity, a kind of magnetic cocoon in the relentless flow. But our shield is not impervious, nor is it meant to be. It is designed to interact. The magnetosphere channels and guides. When the solar wind, carrying the sun's interplanetary magnetic field, flows past Earth, it compresses the day side of our magnetic field and stretches the night side into a long, flowing magnetotail. Some of the energized particles from the solar wind manage to slip through the magnetic defenses, primarily at the polar cusps, funnel-shaped regions near the magnetic poles. They are drawn down along the magnetic field lines, spiraling toward the atmosphere over the Arctic and Antarctic circles. And here, in the thin, high air about 80 to 300 kilometers above the ground, the magic happens. These speeding solar particles, mostly electrons, collide with atoms and molecules of oxygen and nitrogen in our upper atmosphere. The collision transfers energy, exciting these atmospheric atoms. Like a tiny light bulb switching on, each excited atom then releases that extra energy by emitting a photon of a specific color. Oxygen emits a greenish or sometimes a deep red light. Nitrogen emits blues and purples. This is the aurora, the northern lights, aurora borealis, and the southern lights, aurora australis. The result is a silent, celestial ballet. Great undulating curtains of light, shifting from green to pink to violet, shimmering and folding as if moved by a gentle, cosmic breeze. They can appear as slow-moving arcs, as pulsating globes, or as rushing coronas directly overhead. They are the visual proof of the conversation between the sun and the earth, a conversation conducted in the language of magnetic fields and charged particles. They are not a weather of our lower atmosphere, but a space weather painted on the highest canvas of our sky. This phenomenon is a constant, but its intensity varies with the solar cycle. During solar maximum, when coronal mass ejections and fast solar wind streams are more frequent, the auroral oval expands, and the lights can be seen much farther from the poles, sometimes blessing temperate latitudes with their otherworldly glow. Throughout history, these displays have been sources of wonder, myth, and sometimes fear. Today, we understand them as a beautiful and benign side effect of our planet's vital magnetic shield doing its job. So, as you rest, consider these two journeys. The swift, straight-line journey of the photon, bringing you the sun's ancient, steady news in the form of light and warmth, and the slower, winding journey of the solar particle, caught in Earth's magnetic embrace and transformed into a shimmering veil of color in the cold, high dark. One feeds your eyes and your world. The other paints a dream upon your night. Both are born from the same dynamic star. They remind us that our planet is not an isolated island, but an engaged participant in a flowing, energetic system. We are touched by the sun in more ways than one, by its light that defines our days, and by its wind that, on certain clear, cold nights, writes its greeting across the stars in luminous, dancing script. From the ethereal dance of auroras in the polar night, let us return to the solid ground beneath our feet, to the green leaves on the trees, to the very rhythm of our breath. We have followed the sun's energy across space as light and wind, witnessed its most dramatic performances. But its most profound role is not in these distant spectacles. It is in the silent, daily, life-giving miracles that unfold in every cell of every living thing on Earth. The sun is not merely our nearest star. It is the indispensable heartbeat of our biosphere, the quiet architect of our climate, the gentle timekeeper of all life. Let us explore how this distant ball of plasma is, in fact, the closest and most essential participant in the story of life on our pale blue dot. It begins with photosynthesis. This word, often reduced to a diagram in a textbook, is perhaps the most important biochemical process on our planet. It is the alchemy that turns sunlight into substance. Within the chloroplasts of green plants, algae, and some bacteria, molecules of chlorophyll capture the photons of sunlight. This captured energy splits water molecules and powers the assembly of carbon dioxide from the air into simple sugars. The equation is deceptively simple. Sunlight plus water plus carbon dioxide equals glucose plus oxygen. But this process is the foundation of the entire planetary food web. Every calorie of energy in every piece of fruit, in every grain of wheat, in every leaf eaten by an herbivore, and in every carnivore that preys upon them, is ultimately sunlight captured and transformed. The oxygen we breathe, every molecule of it, is a waste product of this magnificent solar-powered chemistry. When you take a breath, you are inhaling the sun's gift, produced by a leaf somewhere, sometime. We are, in the most literal sense, beings of sunlight, our bodies built from and powered by energy that began its journey in the solar core. But the sun's role extends far beyond the dinner plate. It is the great regulator of our climate. The Earth is in a delicate thermal balance. It absorbs shortwave radiation from the sun, mostly visible light, and re-radiates it back into space as long-wave infrared radiation. Our atmosphere, with its blankets of greenhouse gases like water vapor, carbon dioxide, and methane, traps some of this outgoing heat, creating the natural greenhouse effect that keeps our planet habitable. Not a scorching Venus nor a frozen Mars. The sun's steady output sets the baseline temperature for this entire system. The sun also drives the weather. The unequal heating of the Earth's surface, more at the equator, less at the poles, creates temperature gradients. Warm air rises, cool air sinks. This movement, combined with the planet's rotation, generates the global circulation patterns of the atmosphere, the trade winds, the jet streams, the great high and low pressure systems. Every breeze that rustles the leaves, every monsoon that brings life-giving rain, every gentle sea breeze is a direct consequence of solar heating. The sun is the engine of the atmospheric engine. This leads us to the hydrological cycle, the grand journey of water. Solar energy provides the heat that evaporates water from oceans, lakes, and soil. This water vapor rises, cools, condenses into clouds, and falls back to Earth as precipitation. Rain, snow, sleet. This cycle, powered entirely by the sun, distributes fresh water across the continents, fills rivers, sustains forests and farmlands, and carves landscapes over millennia. The water you drink today has been evaporated by the sun countless times in Earth's long history. It is a solar distilled gift. Beyond the physical, the sun governs the biological clocks of almost all life. The reliable 24-hour cycle of light and dark has hardwired a rhythm into the biochemistry of living organisms. The circadian rhythm. In humans, this internal clock, synchronized by sunlight hitting specialized cells in our eyes, regulates our sleep-wake cycle, hormone release, body temperature, and even gene expression. The morning light tells our bodies to suppress melatonin and produce cortisol, waking us up. The evening dimness reverses the process, preparing us for sleep. Our very health is tied to this daily solar cadence. The seasonal changes in day length, photoperiod, trigger migrations, hibernations, flowering, and reproduction in countless species. The sun is the conductor of life's great seasonal symphony. Even the geology beneath us bears the sun's indirect signature. The climate it drives influences rates of weathering and erosion. The life it supports, like plants that break down rock, shapes the very soil. The fossil fuels we burn, coal, oil, natural gas, are the stored, ancient remains of sunlight captured by plants and algae millions of years ago. We are burning concentrated, fossilized sunlight to power our civilizations. Consider the profound integration. A tree grows by photosynthesis. Sunlight, its transpiration contributes to local humidity, solar-powered water cycle. It provides shelter from the sun and wind, solar-driven weather. Its leaves fall and decompose with the seasons, solar-governed cycles, and it may one day become coal, fossilized sunlight. Every thread of the tapestry of life is spun from solar energy. So, as you listen, feel this deep, nurturing connection. The warmth on your skin is not just a sensation. It is the energy source for the planet. The air in your lungs was freed from water molecules by sunlight. The food that fuels your body is packaged sunlight. The rhythm of your sleep is set by the sun's journey across your sky. You are a solar-powered, solar-timed being, living on a solar-watered, solar-warmed world. The sun is not a distant, indifferent astronomical object. It is an active, nurturing presence. Its constancy has allowed life to evolve in complexity over billions of years. Its variations, like the gentle pulse of the seasons and the day-night cycle, provide the predictable patterns that life thrives upon. In this quiet moment, you are the current conscious expression of a relationship 4.5 billion years in the making. A relationship between a rocky planet and its star, a story written in chlorophyll, in rainfall, in genetic code, and in the quiet, steady beat of your own heart, synchronized to the rising and setting of our local star. We are children of the sun in every conceivable way. After immersing ourselves in the sun's life-giving embrace, its light fueling our world, its rhythms ordering our days, we must gently turn to a more nuanced aspect of our relationship. For all its constancy and nurture, our star is not without its moments of tempest. We have glimpsed these in the flares and coronal mass ejections. While they paint our skies with auroras, they also remind us that we live within the atmosphere of an active star, subject to its weather. This space weather, when severe, can ripple through the delicate technological web we have spun around our planet. Yet, understanding these ripples is not a cause for fear, but for mindful awareness, a recognition of the forces we live with and the quiet resilience we cultivate in response. Let us explore these potential disturbances with a sense of perspective and calm. The root of these disturbances is, as we've learned, the sun's dynamic magnetic field. When a coronal mass ejection or a high-speed solar wind stream is directed toward Earth, it carries with it a powerful, tangled magnetic field and a flood of energetic particles. When this cloud collides with Earth's magnetosphere, it can transfer enormous energy into our magnetic shield, causing it to shake and vibrate, a geomagnetic storm. These storms are graded on a scale, much like hurricanes or earthquakes, from minor to extreme. It is during the extreme events that our technology feels the effects. The most famous historical example is the Carrington event of September 1859. Named after the astronomer who observed the colossal solar flare that preceded it, this was a perfect solar storm. A massive CME traveled to Earth in just over 17 hours, much faster than the usual few days, and struck our magnetosphere with unprecedented force. The results were both spectacular and, for the technology of the time, deeply puzzling. Telegraph systems, the Victorian internet, failed worldwide. Operators received electric shocks, telegraph papers caught fire, and some lines continued to operate even after being disconnected from their power supplies, powered solely by the currents induced in the wires by the fluctuating magnetic field. Auroras were seen as far south as the Caribbean and Colombia, so bright that people could reportedly read newspapers by their light in the middle of the night. It was a breathtaking display of our planet's connection to the sun and a hint of potential vulnerability. In our modern, hyperconnected world, the impacts of a similar event would be more widespread, though not apocalyptic. Let's walk through them calmly. Power grids. This is the most significant concern. The rapidly shifting magnetic fields during a severe storm can induce powerful geomagnetically induced currents, GICs, in long conductors on the ground, primarily in high-voltage power transmission lines and pipelines. These DC-like currents can overload transformers, the massive, expensive, and difficult-to-replace hearts of the electrical grid. They can cause overheating, internal damage, and even complete failure. A prolonged, wide-area blackout could result not from a lack of power generation, but from the crippling of the distribution network. Grid operators are aware of this risk and have protocols to mitigate it, such as temporarily taking vulnerable systems offline during a storm warning. Satellites in Earth orbit are on the front line of space weather. Energetic particles can penetrate their electronics, causing single-event upsets, bit flips in memory or logic that can disrupt or disable systems. Over time, this radiation can also degrade solar panels and other components. During intense storms, the upper atmosphere heats and expands, increasing drag on satellites in low Earth orbit, which can alter their orbits and require more fuel for station keeping. Satellite operators design for these conditions with shielding and redundant systems, and they can put sensitive instruments into safe mode during alerts. Radio communications and navigation. The ionosphere, a layer of our upper atmosphere ionized by solar radiation, is crucial for reflecting certain radio frequencies over long distances. A geomagnetic storm can disturb the ionosphere, causing radio blackouts on the sunlit side of Earth, particularly affecting high-frequency, HF, communications used by aviation, shipping, and amateur radio. The storm can also create scintillations, ripples, in the ionosphere that distort the signals from global navigation satellite systems, GNSS, like GPS, reducing accuracy for hours or even days, affecting everything from precision agriculture to navigation systems. Astronauts and high-altitude aviation. For astronauts outside the protective bulk of Earth's magnetosphere, such as on a mission to the Moon or Mars, or even for those on the International Space Station, which is still within the magnetosphere but exposed to higher doses, especially during crossings of the South Atlantic anomaly, solar particle events pose a genuine radiation health risk. Similarly, crew and passengers on polar flight routes, which cross near the magnetic poles where shielding is weaker, can receive elevated radiation doses during a storm. Flight paths are sometimes adjusted during significant events as a precaution. It is important to breathe and hold these facts lightly. Extreme Carrington-level events are rare, estimated to occur perhaps once every few centuries. We are not helpless. A global network of spacecraft like NASA's Solar Dynamics Observatory, the ACE satellite at the Lagrangian L1 point upstream from Earth, and the NOAA Space Weather Prediction Centers constantly monitor the sun. They provide crucial warnings, often days in advance for CMEs, and minutes to hours for solar flare radiation. This allows for preventative actions. Grid operators can reconfigure systems, satellites can be safeguarded, and sensitive missions can be postponed. Furthermore, our technology and infrastructure are becoming more resilient. New transformers are being designed with GIC mitigation in mind. Spacecraft electronics are increasingly radiation hardened. We are learning, adapting, and building with an awareness of our cosmic environment. So, as we consider this, let's reframe the perspective. The potential for solar storms is not a flaw in our relationship with the sun. It is simply a parameter of it, like the potential for a severe thunderstorm on Earth. We build lightning rods and weather-resistant structures. Similarly, we are learning to build a society that can weather solar storms. These events underscore that we are not separate from our cosmic environment. our technology has woven a new layer, a delicate electromagnetic skin, over the planet, and this skin is sensitive to the solar wind. This sensitivity is a sign of our advancement, but also of our connection. The same solar wind that could induce a damaging current is the very wind that creates the protective magnetosphere and the breathtaking auroras. It is all one system. By understanding and respecting the sun's full nature, its nurturing constancy, and its occasional powerful size, we deepen our relationship with it. We move from passive recipients of light to conscious inhabitants of a solar system, learning to live in harmony with the gentle and sometimes powerful rhythms of our home star. The risk is real, but so is our growing wisdom and preparedness. It is a quiet dance of awareness and adaptation under the same ancient, golden light. Having navigated the gentle ripples of solar storms and our technological kinship with them, we now turn our gaze forward, not to tomorrow or next year, but across a gulf of time so vast it redefines our understanding of future. We have traced the sun's story from its birth in a cloud of ancient stardust to its current, steady middle age. But every story has an ending, and the sun's is written in the same nuclear physics that gives it life today. This ending is not an abrupt catastrophe, but a slow, majestic, and inevitable transformation. It is the natural conclusion of a star's life, a process that will unfold with the serene slowness of geology and the breathtaking beauty of cosmic recycling. So, let us contemplate the distant fate of our sun, not with sorrow, but with a sense of profound, peaceful awe for the grand cycles of the universe. Our sun is currently in the prime of its life, a stage astronomers call the main sequence. Here, it fuses hydrogen into helium in its core, maintaining a perfect balance between gravity's inward crush and fusion's outward push. This stable phase is extraordinarily long-lived. The sun has been in this state for 4.6 billion years, and it has about 5 billion years of hydrogen fuel remaining in its core. 5 billion years. To grasp this, consider that complex life on Earth has existed for only about 600 million years. All of human history is but a blink in the duration of the sun's remaining stable life. We are living in the long golden afternoon of a stellar day that will last nearly 10 billion years in total. But nothing lasts forever, not even a star's core. As the eons pass, the core gradually becomes enriched with helium, the ash of hydrogen fusion. This helium is inert under the core's current conditions. Eventually, in roughly 5 billion years, the hydrogen in the core will be nearly exhausted. With no fusion to provide outward pressure, the core will begin to contract under its own weight. This contraction releases gravitational energy, heating the core even further. This new, intense heat ignites a shell of hydrogen fusion around the inert helium core. The energy from this shell fusion pushes the sun's outer layers outward with tremendous force. The sun will begin to swell. It will leave the main sequence and enter the red giant phase. It will expand, slowly and inexorably, to a diameter perhaps 200 times its current size. From Earth, the sun would no longer be a discrete disk in the sky. It would fill a large portion of the heavens, a bloated, glowing orb of deep red or orange. Its luminosity will increase 1,000-fold. During this expansion, it will almost certainly engulf the inner planets. Mercury will be vaporized. Venus will follow. And Earth? The fate of our world is not perfectly certain, but the odds are against its survival as a solid planet. Even if it isn't fully swallowed, its surface will be scoured clean, its oceans boiled away into space, its very rocks melted. The beautiful, delicate biosphere we know will have been gone for eons, a distant memory in the rock record of a long-dead world. This is not a violent act of destruction, but a simple, inevitable consequence of the star's growth, like a tree's roots eventually cracking a sidewalk placed too close to its trunk. Meanwhile, in the sun's heart, the story continues. The contracting helium core will heat to an astonishing 100 million degrees Celsius. At this temperature, a new fusion process ignites, helium fusion. In an event called the helium flash, the core will fuse helium into carbon and some oxygen in a thermal runaway that lasts only minutes, but which fundamentally changes the star again. For a time, the sun will find a new, temporary equilibrium, fusing helium in its core and hydrogen in a shell around it. It may even shrink back slightly, becoming a little hotter and yellower for a while, in a phase called the horizontal branch. But this stability, too, is fleeting. Helium fusion is a faster, more profligate process. Within perhaps 100 million years, the helium in the core will also be exhausted, leaving a core of carbon and oxygen. The core will contract again, and a shell of helium fusion will ignite around it, which itself is surrounded by a shell of hydrogen fusion. The sun will swell once more, becoming an even larger, more luminous red giant, an asymptotic giant branch AGB star. It will become highly unstable, pulsating in brightness and shedding its outer layers in powerful, dusty winds. This is where the sun creates its most beautiful legacy. Over tens of thousands of years, these gentle but persistent stellar winds will blow away the sun's entire outer envelope, a vast shroud of gas and dust, enriched with newly forged carbon and other elements. This expanding shell, illuminated from within by the hot, exposed core, will glow as a planetary nebula. The name is a historical misnomer. It has nothing to do with planets. It is one of the most exquisite sights in the universe. A luminous, often symmetrical bubble of gas, visible across interstellar distances, a final, radiant sigh. What remains after this great exhalation? The sun's core, no longer supported by fusion, it will collapse under gravity until it is stopped by a quantum mechanical force called electron degeneracy pressure. It will become a white dwarf, an Earth-sized sphere of incredibly dense matter. A single teaspoon of white dwarf material would weigh as much as an elephant on Earth. This white dwarf will be intensely hot at first, perhaps 100,000 degrees Celsius, glowing white-hot from its residual thermal energy. But with no internal furnace, it will slowly cool over billions upon billions of years, fading like a dying ember in a cosmic fireplace, eventually becoming a cold, dark black dwarf, a crystalline carbon cinder drifting through the galaxy. The planetary nebula around it will have long since dissipated, its atoms recycled into the interstellar medium, destined perhaps to become part of new stars, new planets, and maybe new life. So, as you rest in the present, let this far future settle softly in your mind. It is not an end, but a transformation. The atoms that make up your body, the earth, and everything you know are stardust. And in the distant future, they will return to that cycle. The sun's fate is not a tragedy. It is the standard, graceful life cycle of a star of its modest mass. Its death will seed the galaxy with the elements necessary for future worlds. This immense timeline puts our moment in perspective. We exist in a golden, stable epoch, a precious sliver of cosmic time where the sun is gentle, Earth is habitable, and life can flourish. We have billions of years of steady sunlight ahead. The distant red giant phase is a reminder not of impending doom, but of the incredible, dynamic story we are a part of. We are living in the chapter where the star shines steadily, the planet is blue and green, and consciousness has emerged to look up and wonder. It is a chapter to be cherished, a peaceful, prolonged afternoon in the life of our solar system. The sun's quiet farewell, billions of years from now, will be a spectacle of cosmic recycling, a beautiful and necessary part of the great story. But that story is for a future universe unimaginably different from our own. Our story is here, now, in the gentle, constant glow of a middle-aged star that holds us in its warm, gravitational embrace, lighting our days and guiding our seasons. For all the eons to come, within the span of life on Earth, the sun will remain our faithful, steady hearth in the cold cosmic night, a promise of dawns to come for billions upon billions of tomorrows. And so our quiet exploration comes to a gentle close. We have journeyed from the galactic suburbs to the solar core, from the first fusion of a proton to the last sigh of a planetary nebula in the far, far future. We have traced the paths of light and wind, felt the pulse of magnetic fields, and marveled at the star that is both our creator and our constant companion. It is a story of unimaginable scales and profound intimacy, a reminder that we are woven into the fabric of our star, and it into us. Now, let all those vast concepts, the millions of degrees, the billions of years, the million-mile winds, soften and recede like distant mountains fading into an evening haze. Release them. They are the backdrop. Bring your awareness back to this quiet moment, to the rhythm of your own breathing. In and out, steady. The same sun whose epic tale we followed is, at this very moment, simply a promise on the other side of the world. It is holding its light in trust for your dawn, keeping its warmth in reserve for your tomorrow. There is a profound peace in that certainty. Feel the gentle weight of your body resting, supported. The same gravity that holds the planets in their graceful orbits holds you here, now in safety. The same atoms forged in ancient stars make up the quiet air in this room. You are not separate from the cosmos. You are a cherished part of its ongoing story, a story that, for our chapter, is characterized by a remarkable stability, by the dependable arc of a yellow sun across a blue sky, by seasons that turn in a reliable cycle, by the daily gift of light that feeds and warms a living world. Let your thoughts settle like dust motes in a sunbeam. There is nothing more you need to hold, nothing more to solve. The sun does not strive. It simply shines. It exists in a state of perfect, patient balance. And in this moment, you can too. Allow the night to hold you. If your window is open to the sky, know that whether you see stars or clouds, the silent influence of our sun is there. In the dark, it is the reason for the dark. In the reflected moonlight, it is the original source of that silver glow. It is always present, a steady heartbeat in the chest of the solar system. So, as sleep draws near, let your mind be a calm sea reflecting that steady light. No storms, no waves, just a deep, still peace. The journey is complete. The facts become dreams. The voice becomes a whisper. The universe is vast, but in this corner of it, all is well, all is quiet, and you are safe. The sun has done its work for today, and so have you. Now it is time to rest. Let go and drift on the quiet current of the night, knowing you are forever cradled in the gentle, timeless embrace of a story much larger than yourself. A story that continues softly, even in your dreams.